Hello everyone and welcome back. In today's video, titled Material Substitution in and for Conventional Lithium-ion, I'll be discussing how we can reduce our dependence on critical materials by introducing material substitutions as well as exploring alternative battery chemistries. As you saw from our last videos, lithium-ion batteries have become an integral part of modern life, powering everything from our smartphones and laptops to the growing number of electric vehicles on our roads. However, as demand for these batteries continues to increase, ensuring a stable and sustainable supply has become a key challenge. In this session, I will highlight 3 key strategies, among many others, to reduce dependence on critical materials such as cobalt, nickel, and lithium. Some of these are already in use, and others are currently being actively researched. The first strategy, already implemented by industry, involves using alternative lithium-ion cathode chemistries. This entails the substitution of lithium nickel cobalt manganese oxide, or the NCM cathode, with the lithium iron phosphate, or LFP1. This change comes with a trade-off in energy density, as LFP batteries typically have a lower energy density than NMC. However, LFP offers notable advantages in terms of safety, thermal stability, and cycle life, making it a viable and increasingly popular alternative. This replaces the more critical cobalt and nickel containing NCM with an iron containing compound, which is much more abundant. The second strategy focuses on developing battery technologies that use alternatives to lithium, such as sodium. Sodium is the 6th most abundant element, making it much easier and cheaper to source than lithium. This makes sodium-ion batteries a promising alternative, especially for large-scale energy storage where keeping costs low is important. But why would a sodium for lithium substitution work? First of all, sodium and lithium are in the same group on the periodic table, so they both share similar chemical properties. This means that they can both insert or intercalate in battery electrodes. This means that sodium can be used in a similar battery designs as lithium. But it's not that easy, as there are some differences. Sodium ions are much larger than lithium ions, so battery materials need to be adjusted to fit them. Also, sodium-ion batteries have a lower energy density, meaning they store less energy, which makes them better suited for large-scale storage rather than small devices or high-performance electric vehicles. Now, the final strategy is the exploration of alternative battery chemistry, often referred to as the post-lithium ion or next-generation batteries. I have chosen 2 representative chemistries that are effectively being investigated by researchers. These are the lithium-sulfur and the lithium-air batteries. Lithium-sulfur batteries consist of a metallic lithium anode and a sulfur cathode. During discharge, sulfur at the cathode is reversibly transformed into lithium sulfide, and during charge, lithium sulfide is converted back to sulfur. Lithium-air batteries, on the other hand, also have a metallic lithium anode, but the cathode uses oxygen from the air, which enters the battery through a gas diffusion electrode. During discharge, oxygen undergoes a reduction reaction, forming lithium peroxide at the cathode, but during charge, lithium peroxide decomposes in an oxygen evolution reaction, releasing oxygen and regenerating lithium. Lithium-sulfur and lithium-air batteries offer significantly higher energy densities than conventional lithium-ion batteries, making them potentially attractive for applications requiring lightweight and long-lasting power sources, such as electric vehicles and aerospace systems. Additionally, these chemistries avoid the use of critical and expensive metal such as cobalt and nickel, which are commonly found in traditional lithium-ion cathodes, thus offering potential cost and sustainability benefits. However, despite their promise, key challenges remain for both battery chemistries. They exhibit limited cycle life due to material instability, such as the dissolution of intermediates in lithium-sulfur batteries or the clogging of the gas diffusion layer in lithium-air systems. Moreover, they still rely on metallic lithium, which poses safety risks due to dendrite formation, and concerns remain about resource availability and battery handling. Well, now all that being said, I hope I've convinced you that by using LFP instead of NCM in batteries helps reduce dependence on critical and expensive materials like cobalt and nickel. Sodium-ion batteries, which share similar chemistry with lithium-ion, offer a more sustainable alternative by using sodium which is the more abundant and cheap resource. While next generation battery technologies like lithium sulfur or lithium air are promising, they still face technical challenges and require further development before they can be widely adopted.